Alright, in this video we're going to look at the Compton effect / the Compton scattering. So we have incoming here a photon, and this photon here is a photon of light, and coming out here we have a photon and this here, this electron. So in the metal itself, if you zoom in to this little spot here, zoom in, there's an electron, and when the photon comes in, it hits the electron and sort of ricochets off. Okay, so let's say electrons like this, it ricochets off, and yet the electron bounces off. So what this is just simply a plastic collision. Okay, basically you're finding the energy of this electron and of this electron and of this photon, and you're making sure that all the energy in the total system is equal to this energy at the beginning. Okay, so we know that the electron here has an energy because now it's got an EK, it's moving, it's got a velocity. Okay, so it's got an EK, which means that our photon on this side here has to have a smaller amount of energy than initially did. Okay, so energy, if we remember correctly, is energy for a photon is hf, or the other option is hc over lambda. Okay, so if our original wave here is coming in really tightly wound waves like this, okay, then our output wave, oh my goodness, what's going on? Our output wave has to have really long. Okay, so basically the idea is that our wavelength increases because our energy has to decrease. So because we know, I'm going to call this energy photon in, energy photon out, maybe final. Okay, so we know that our energy of the photon in has to be greater than the energy of the photon final. Okay, and we know that because if all the energies are equal, at the end we have some sort of we have this EK here. Okay, so that's what's taking away that energy. It's a wasted energy, you could say. So since this equation is true, we can also then bring it down and substitute in, instead of having E on either side, we could have HF on either side, or we could have HC over lambda on each side, HC over lambda. And if you simplified those down, you could get rid of the H. So here, let's call this Fi, Ff, I, Ff. So now if we wrote them out again, Fi is greater than Ff, and for lambda, it's lambda F is greater than lambda I. So that's one way of looking at what's going on here. And Compton said that since this is happening, we know that there's a collision. It doesn't make sense if there is no collision happening here, then this doesn't work. Okay, this doesn't make a whole lot of sense otherwise. Okay, so he actually did this a bunch of times and figured out this is his equation. So the lambda final is minus lambda initial, or some notations have it lambda prime minus lambda equals, I'm just going to write like the top one here, HMEC. Okay, so this is Planck's constant, mass of an electron, the electron that's you're jettisoning out, this green one here. Okay, mass of an electron times by 1 minus cos theta. Well, what's that theta? Well, if we look here, this would be your theta. Okay, so that's your theta, or if we look here, this is your theta. Okay, so it's the change in direction from the original direction of the photon. Originally it was coming in like this, straight, and then it changed, and now it's going like this. So that angle difference is theta. Okay, and that is our equation. So that is the Compton scattering equation, and hope that explanation helps somewhat. It's looking at definitively looking at light. Is it a particle or a wave? And this is the first definitive proof that light has particle properties. And Compton finally proved that particle side of light, and that's super important. And now we have an equation because of it. Hope that helps, and good luck on Compton effect / scattering.